Okay, Assalamualaikum and good morning everyone. So as for today, we will be continuing our lesson, okay, which we are going to look into the RC beam design. Okay, right. So as usual, okay, we are going to start our class, okay, with Kitab Al-Fatihah. Okay, right. So as for today, okay, we are going to look into the basics, okay, of RC beam design. Right. So beam is a structural element, okay, that is designed to resist bending moments, okay, shear force, torsions, and also their combinations. Okay, so beam, okay, is to support slabs, okay, and then it also supports secondary beams, okay, and also columns, if any, right, and it is also used to support brick walls, okay, roof trusses, okay, if we are talking about roof structures, okay, roller shutters, okay, water tanks, and etc. Right, okay, so we have a variety of function, okay, of a beam, okay, and it is usually meant for support. Right. Okay. So usually, if we talk about the slab, okay, that we have already designed previously, right? Okay. So the supports for slabs, okay, must be the beams, okay, especially for the restrained slab. Okay, so it is also to ensure, okay, that to ensure the beam behaves satisfactorily when loads are applied. So therefore, the ultimate limit state or ULS and serviceability limit state has to be taken into consideration during the design, right? So this is actually similar to what we have already used in the design of a slab. Right, so we will start, okay, with the calculation, okay, of the main reinforcement, which is under ultimate limit state. Okay, and then we are going to check our design under serviceability limit state. Right, so it goes the same way for the beam design as well. Right, so if you look here, okay, so these are the complete beam design procedure. Right, okay, so these are actually similar to what I have already briefed to you, okay, before when we go through the analysis of sections, okay, of structural element. Okay, right. So we can see here that the first step is to determine the nominal cover and also the section dimensions. Right. Okay, so basically when we talk about the nominal cover, right, so this is covering on the durability requirements. Okay, right. So I have already explained to you that we have the exposure conditions, okay, then we also have fire resistance requirement, right? So those are the requirements that we are going to use to determine the nominal cover, right? Okay, then the next one, okay, is also is on the section dimensions. Okay, so basically the sections dimensions, okay, is with regards to the estimation, okay, estimation of the size of our element. Okay, so how big is our element, right? So therefore we have to determine this based on the section dimensions. Okay, then calculation of the effective depth, okay, which is based on the assumed bar size, right? So this is actually almost similar to the beam design, right? To the slab design. Only that now, okay, when we are talking about the effective depth for a beam design, we will be considering the links as well, right? Okay, so we are going to have one additional element, okay, which is the links, okay, or the shear reinforcements. Okay, so next one is the design load calculation, okay, whereas you are going to look into the load pattern, right? Okay, so for the beam, since it is a support element, okay, which usually supports slab, okay, so therefore we are going to also learn on how to transfer the loads from the slab to the beam. Okay, right, then only we are going to calculate, okay, and also do the analysis. Right, okay, so the analysis is where we are going to draw the shear force and also bending moment diagram. Okay, and as what we have already learned earlier, right, okay, where in your syllabus, you are going to look into the shear force diagram and also bending moment diagram envelope. Okay, whereas will be considering the critical values, okay, or critical arrangement of the loadings, okay, in order to get the most critical shear force and also bending moment. Okay, then the next one is the design, right? Okay, so as what I've mentioned earlier, right, okay, is that we are going to consider the ULS as well as SLS, right? Okay, so we have two limit states, okay, that we have to consider in the design. So for under ULS, okay, we are going to design the main reinforcements as well as design the shear reinforcements, okay? All right, so as for the SLS, okay, so we are going to have the deflection check and also we have the crack check, right? So basically we are going to just do the calculation, okay, but not the detailed calculation of the deflection or the crack width. Okay, right. So the next one, okay, which will be another topic, okay, in your syllabus, okay, is the torsion reinforcement. Okay, however, we are going to look into this in particular, okay, for the topic that is for torsion design for beams, right? Okay, so we have one topic that is particularly for this, okay, because this is something new to you, right? So you have not looked into this earlier in your diploma program, right? Okay, so you do not have this. So this is another part, okay, of the design in the design of NRC beam. Okay, right. So the next one is on the detailing and also curtailment, right? Okay, so I have already briefed to you some part of this, okay, which is with regards to the curtailment rules, okay, that we have to follow when we are designing a simply supported beam and also when we are designing a continuous beam, right? Okay, so we are going to look into that as well, okay, in the detailing, the drawing of the detailing. Right. Okay. So it needs to have a correct direction. Okay. It needs to have correct coverage, and also the reinforcement has to be in the correct direction, correct location. Right. Okay. So if it is to cater for the tensile forces, so therefore it has to be within the tensile region. Okay. And if it is meant to cater for the compressive forces, right? So it needs to be at the correct location, right? So you cannot make mistake on this, okay, because this is the main medium, okay, that we wanted, that we are going to use, okay, in order to communicate with the contractors. Okay, right. So loadings transferred from supported structures, right? So basically we are going to look into the loadings, okay, that is transferred from the slabs, right? Okay, which will be depending on the geometry of the slab, okay, the type of the supported conditions and also the continuity of the slabs itself, right? Okay, so we are going to look into whether the slab that is supported by our beam, okay, whether it is a one-way slab, okay, or it is a two-way slab, okay, because the transfer, okay, the method of transfer and also the value that is transferred to the beam, okay, will be different, okay, depending on the type of slab, okay, that we have, okay, whether it is one-way or two-way slab. Okay, right. Then also we are going to look into actions from columns, right? So actions from columns. This is only for the case if our beam is supporting a column, right? Okay, it means that we have a column that is sitting on top of our beam, right? Okay, so it is known as uh, a supporting beam, right? Okay, so we are going to have the beam. Okay, so if I can draw here, right? Okay, so we are going to have the column, okay, that is sitting directly on top of our beam, right? Okay, so therefore this will be inducing the loads, okay, to our beam, right? Okay, and as for this beam, okay, we have the load, we have the support, right? Okay, so and it is supporting I cannot really remember the term. Okay, so we have the column that is sitting on a beam. Okay, so the loading is not transferred directly to the foundation. However, it is transferred to our beam. So if we have this type of case, okay, so what we are going to have, okay, is that we are going to be having the point load. Okay, so this point load will be acting on top of our beam, right? So there are also cases that looks like this. Okay, then another one, okay, that we can also consider, okay, the actions that is from the staircase, right? So just now we have one is the loading from the slab. Okay, then we also have the actions from the column. Okay, and then we also have the actions that is from the staircase, right? So when we are considering the actions that is from the staircase, actually we are almost considering that we are transferring the loadings that is from a slab, right? Okay, so as you can see here, okay, this is where we have the loadings that is from the staircase, right? So we are transferring the loads, okay, to the from the staircase, okay, to the support, right? So if you see here, so this will be the support for our staircase, right? Okay, so it is connected at that point. Right, so we are going to also learn, okay, if we have to transfer the loads, okay, in that particular manner. Okay, then the next one is also the action from the brick wall. Okay, so if we have any brick walls that is sitting on top of our beam, right, so therefore we have to consider the loadings as well, right? Okay, so for example, if we have this, okay, so you can see here, okay, that we have the brick walls. Okay, right? So when the brick wall is sitting there, right? So therefore you need to consider the thickness, okay, and also the density of the type of bricks, okay, that we are using. Okay, because we have a variety of the types of bricks. Okay, so we have the clay bricks, okay, and also we have the lightweight bricks, right? So you need to consider, okay, what type of bricks that we will be using for our construction. Okay, right. So these are the examples, okay, of loadings that will be transferred to the supported structures. Okay, right. So the analysis of structure, okay, which is under ULS, okay, if we are considering the continuous spans, okay, so for RC structure, okay, the continuous beam is a monolithic frame, right? So when we talk about monolithic frame, means that it is connected together, okay, between support to support. So we need to obtain the worst condition, okay, for all critical locations. Okay, right. So this is what I have already mentioned to you earlier. Okay, whereas we are considering the moment envelope, okay, and also shear envelope. Right. So we need to determine the M value, the V value, and etc. Okay, and also we need to determine whether the bending moment that is acting on our beam is a sagging or hogging bending moment. Right. Okay, so this is very critical. Okay, since we need to determine whether the main reinforcement will be placed at the bottom or on top of the beam. Okay, right? Okay, so the location of the reinforcements is also very important. Okay, so the loads that we will be considering for the beam, okay, will be the permanent actions as well as variable actions. Okay, so for the permanent actions, okay, it covers all parts of the structure, okay, which we are going to consider all spans, okay, at all times. Okay, right? So it means that we will always have this permanent action, okay, regardless of the alternate loadings, okay, that we are considering in our beam. Okay, right. Okay, so that is for the permanent actions. Okay, so we are considering this, okay, because when we talk about permanent actions, usually we will be talking about the self weight of the structure itself, right, which it will always be there, right, and also we will be considering other permanent elements. Okay, for example, finishes, right? So finishes are also considered as permanent loadings, right? So it will be staying, it will be there, okay, throughout the life of the structure, right? So that is why, okay, with regards to the permanent actions, we will be considering this to cover all parts of the structures. Okay, then as for the variable actions, okay, it can usually cover all or any part of the structure, okay, where we are going to consider several span at certain duration. Okay, right? So as for the variable actions, okay, it can be provided alternately. Okay, so for the load patterns, okay, there are many possible load cases, okay, where we need to consider all possible patterns, okay, to obtain the worst condition. Okay, so each MDM, okay, or subframe, for each case, okay, we are going to do the moment distribution method, okay, or subframe method, okay, and it can be done manually or using the software. Okay, however, it is much more easier, okay, if you can do it using the software. Okay, right? Because if you are doing it manually, right, then it will be requiring multiple calculations. Okay, right? So if you still remember in your analysis subject, right? So with regards to the moment distribution method, right? Okay, so actually the calculation is quite tedious, right? So if you are doing it manually, okay, then after you have done the moment distribution method, okay, for each case, right, then we can superimpose all bending moment diagram and shear force diagram in order to obtain the envelope profile. Right, okay, so basically I have already explained to you this earlier, okay, when we are referring to the Mosley textbook. Right, okay, so you can also refer to that, okay, with regards to how we are going to obtain the envelope profile. Okay, so if the span and support conditions of the continuous beams are able to fulfill the required conditions of table 3.5 from BS 8110, therefore it can be used to obtain the bending moment diagram and also shear force diagram. Right, okay, so however, okay, there are some requirements that we have to follow, then only this table is applicable. However, if the span and support conditions of the continuous beam does not fulfill these requirements, okay, for table 3.5, therefore you need to do the um, manual calculation, okay, or using the software, okay, for the moment distribution method. Okay, then only you will be able to draw the bending moment and shear force diagram. Okay. Right, okay, so with regards to the design, right, so for a normal downstand beam, okay, so at support, okay, which is a hogging moment, okay, therefore at this part, it can only be designed as a rectangular section, right? So you have to bear this in mind. When we are designing for a continuous beam, okay, we are going to only design the support reinforcement or the support beam as a rectangular section, right? Okay, so we are not going to design the support uh, using the flange section. Okay, right. So then at midspan, okay, which is sagging, right? So we know that at midspan, the bending moment will be positive, right? So when the bending moment is positive, therefore we can choose between flange L or T, right? So this is actually depending on the shape of your, the location of your beam, right? Okay, whether it is at the end of the building or it is in the middle of the building. So if it is at the end of the building, all right, so basically we will be designing for L shape, okay, or if it is in the middle of the building, so we will be designing that particular beam as a nice section, okay, or if we have a beam that is standing alone, right, so therefore we are going to design that as a rectangular section. So it actually depends on the location of your beam, right, okay, and also the arrangement of the beam of the continuous beam that you are designing. Okay, so and then for an upstand beam, okay, vice versa. So upstand beam means that the beam is on top of the slab, right? Okay, so the next one is the shear reinforcements design procedure, right? So this is the flow chart, okay, whereas we are going to compute, okay, the values of VED, okay, and then we are going to compare VED with VRDC, right? Okay, so this step, okay, this first step is actually similar to the design of a slab. Okay, whereas we are comparing, okay, in order to determine whether the shear reinforcement is required or not. However, when we talk about a beam, right, so therefore we will be designing the at least, okay, a minimum length for the beam, okay, because beam is considered as more critical in comparison to the slab. Okay, so as for the slab, usually the distribution of the stresses, okay, will be much better, right? Okay, so therefore the value of the shear will be much lower in comparison to the slab. Okay, we need to provide at least the minimum links. Okay, however, checking has to be made, okay, with regards to the comparison between VED and also VRDC. Okay, right? So later when we go through the design, okay, the example, okay, for the design, okay, then only we are going to look into detail, okay, with regards to this design process. Okay, right? Okay, but please bear in mind, okay, that this is the shear reinforcement design procedure. Okay, so the next one is the detailing, right? So you can refer to the EC2, okay, Eurocode 2, Section 9, okay, whereas the detailing, okay, is used to determine the correct locations for the respective design reinforcement, right? Okay, so as what I have already mentioned to you just now, right? Okay, so we need to have the correct locations. Okay, whether the reinforcement, the main reinforcement is to be placed at the bottom or on top of our beam. Okay, then we need to determine also the correct link diameter and spacing as per design. Okay, at the correct and place it at the correct locations in the drawing. Okay, then we also have to calculate and show minimum required encouraged length. Calculate and show minimum required lapping length of reinforcement. Okay, and also reinforcement curtailment. Right. Okay, so when we talk about curtailment, so basically we will be cutting, okay, the reinforcement that is in our beam, okay, in order to avoid any congestion, okay, of the reinforcement, especially at the supports. Okay, right. So we have the curtailment rules. So as you can see here, this is one curtailment rule. Okay, that is for a beam. Okay, for a simply supported beam. Right. Okay, so you can see here that the reinforcement, okay, will be 100%, okay, at the in the middle. Okay, because this is the place where we are going to cater for the bending, the maximum bending moment. Okay, and then towards the end, okay, we can actually reduce our reinforcement to 50%. Right. Okay, and then with regards to the curtailment length, okay, so this is the measurement. Okay, whereas we are going to use 0.08 L. Right. Okay, so that is the maximum value, okay, that we can provide, okay, this 50% of reinforcement, and it goes the same way for both sides since this is a simply supported beam. Okay, then for a continuous beam, right, so you can see here that this is the curtailment rules that we have to follow, right? Okay, whereas we are going to look into the tension reinforcement at the support as well as the tension reinforcement at midspan. So we have two cases here. Okay, whereas when we are talking about tension reinforcement at support, it means that our reinforcement or our main reinforcement will be placed on top. Okay, because we are talking about this part. Right. Okay. So this is the part, okay, where we have a negative bending moment. Okay. So this is the typical curtailment rules. Okay. Whereas when we have what do you call this? The support. Okay. The continuous beam. Right. Okay. So your bending moment diagram will typically look like this. Okay. Okay, right. So your bending moment diagram, okay, will typically look like this. Okay, if we are talking about a typical bending moment diagram, okay, whereas it will be curving like this. So we are going to have sagging moment at the midspan, and we are going to have negative bending moment or hogging bending moment at the support. So what happens here, okay, is that at the support where we have the negative bending moment, so our beam will tend to bend upwards, right? So instead of bending downwards, okay, so our beam, okay, will actually be bending downwards, right? So basically, it will be looking like this. Okay, so I'm exaggerating a bit, okay, with regards to the behavior of our beam, right? So basically, it will look like this, right? So we are going to have supports here and also here. Okay, so with regards to the tension zone, okay, so basically due to the sagging moment, the tension zone or the cracks will happen at the bottom, okay, because it is bending, okay, it is bending downwards, okay, at that positive bending moment. Then at the negative bending moment, basically, okay, the crack, okay, will happen on top, okay, which is this part. Okay, so you can see here, okay, that under sagging moment, okay, the tension zone will happen at the bottom. But when we are talking about hogging moment, the tension zone will happen on top. Okay, then the compression will happen at the other location lah, right? Okay, so as for this, okay, we will be providing the main reinforcement at the place, okay, where our beam is subjected to tension, right? So if this is the case, okay, where the bending moment is positive for midspan, so the main reinforcement will be placed at the bottom. Okay, however, at the support, since the tension zone is happening on top, so therefore the bending reinforcement or the main reinforcement will be placed on top, right? Okay, so that is why, okay, if we are looking at this curtailment rules, okay, so this reinforcement here that we are looking at is the main reinforcement at the support. Right? Okay, so it is sitting on top. Right? So regardless of how detailed your calculation is, if you cannot actually translate this into your detailing, right? Okay, so you are going to transfer a wrong information to the contractors. Okay, that will be building your structure. Okay, right? So you need to have this understanding. Okay, right? Then with regards to the reinforcements that is at the bottom of your beam, okay, so as for this, it will be the main reinforcement for the midspan, right? So this is for the another reinforcement which is placed at the bottom of our beam. Okay, right? So you need to understand this location first, then only we can proceed with the curtailment rules. Okay, right. So now we are going to look into the tension reinforcement at the support. Okay, whereas all bars must be extended with a distance of 0.15 L or 45 diameter from the side of support, whichever is greater. Right? Okay, so we can see here, okay, that we are given this 100%. Right? So 100%, it means that this is the total reinforcement, okay, that you have already designed in your calculation. Right? So 100% of the reinforcement. So maybe it is, for example, 4H20. Right? So that is the 100% of the reinforcement. Then in the rules, okay, it says that at least 60% of the bars must be extended with the distance of 0.25 L from the side of the support. Okay, right. So then after that, okay, after we have already provided this 100% of the reinforcement, okay, then another 60% can be extended further. Right. Okay, so it can be extended further. Okay, with what distance? So the distance is 0.25 L. Right. Okay, so in the common practice, okay, we will be using, usually in the construction, it is using 0.3 L from the center of support. Right. Okay, so because the support of our beam, okay, sometimes it could be uncertain. Right. Okay, so we have various sizes of columns, for example. Right. Okay, so therefore, for the common practice, usually we will be taking the distance, okay, which is 0.3 L. Right, so 0.3 L will be approximately here, right, okay, which is considering to the center of the support. So this is 0.3 L. Okay, so that is for the common practice. Then at least 20% of the bars have to be extended to the end of the span, right? Okay, then we are going to extend, okay, since we also have to provide the hanger bars, okay, for our beam. So therefore, we are going to extend at least 20% of the reinforcement bar to the end of the span. And what is the reinforcement that we will be providing? Is that it has to be more than ES minimum. Right? Okay, so this is the reinforcement. Right? So this is the reinforcement which has to be more than more or equal to ES minimum. Okay, so this will basically be the hanger bar for our beam. Okay, which is for the midspan. Okay, so the next one is for the tension reinforcement at midspan. So this will be the reinforcements that is at the bottom. Okay, right, so we are going to look into this, right? So basically, okay, this is reinforcement 1, right? Okay, so the main reinforcement here is reinforcement 1, and this one will be reinforcement 2. So this is 1 and this is 2. Okay, right. So for tension reinforcement at midspan, all bars at midspan must be extended to a distance of 0.15 L from the center of the interior support and 0.1 L from the center of the outer support. Right. Okay, so we can see here for the bottom part, okay, this is 100% of the reinforcement. Okay, so why is this? Okay, because we have the maximum moment that happens almost in the middle of our beam, right? Okay, which is in this location. Okay, right. Okay, so therefore 100% of the reinforcement is to be provided there. Okay, and then we are going to extend, okay, this reinforcement to 0.15 L from the center of the interior support and 0.1 L from the center of the outer support. right? And then at least 30% of this bar has to be extended to the center of the support, right? So this will be the extension to the next support, right? Okay, which is the uh, reinforcement here, right? So we have 30% here, okay, in the outer support and also the interior support, right? Okay, so that is the way how we can actually design, okay, or transfer, okay, whatever calculation that we have already done, okay, into a drawing, okay, right? And then also we are going to have lappings, okay, right? So as you can see here, okay, in the figure, is that this lapping also have the its own requirements, right? So I will brief this to you later, right? Okay, whereas we are going to provide, okay, this lapping of the reinforcement not at the critical location, right? So we are not going to provide this at the support, okay, with regards to the lapping. So it will be out of the critical areas, right? So however, we need to have a certain dimension, okay, of this lapping, okay, right? So the dimension is actually this length. Okay, so how long, okay, is the length of the beam, of the reinforcements that we are going to provide the lapping, right? So why do we have this lapping, right? So usually we are going to use this lapping if we do not have enough length of our reinforcement, right? So and usually in the on the side, okay, the maximum length, okay, of the reinforcement is usually 12 meters, right? So if it is more than that, usually we will be providing the lapping, right? So in order to actually have a continuous connection actually between the reinforcement, okay, however, we are going to use two separate reinforcements, right? So two separate bars, right? However, we wanted the behavior, the bars to behave um, together, right? Okay, so that is why we are going to have these lappings. Okay, right? So I have already covered, okay, on the detailing, okay, as well as with regards to the design, right? Okay, so this next part, okay, is with regards to the loading transfer. Okay, so this is the loading transfer, okay, whereas we have loading from slab, okay, which is the GK, right? So when we talk about the loadings, the permanent loadings, okay, that is from the slab, okay, so it will be considering the self weight of the slab as well as the finishes that is on the slab as well, okay. And then we also have services, right? Okay, so for example, we have air cons, okay, we have the ceilings, okay, we have the uh, light fixings, okay, right? So all those are known as the services, okay. And then we will be also considering the QK value, okay. So please do remember, okay, that when we are talking about the loading from the slab, okay, these loadings will be in the unit of kilonewton per meter square, right? So it is not UDL yet, okay. However, it is distributed throughout the area of the slab. So we are going to transfer this load, okay, to the beam, okay, that we will be designing. So when it is transferred to the beam, okay, so therefore we are going to change from the area load to line load, right? So area load means that we are going to have our unit in kilonewton per meter square, where we are going to change this to kilonewton per meter. Right, so kilonewton per meter is the loads that is already acting on the beam. Okay, so load distribution from slabs to beam, okay, depends on the geometry of the slab, the type of supports conditions, and also the continuity of the slabs. Right, so we need to look into what is the dimension, okay, of our slab, whether it is a one-way slab or it is a two-way slab. Right, so this is one thing, okay, where we are looking into the geometry of the slab, right? So whether it is one way or it is a two-way slab, then the types of support conditions, right? Okay, so whether it is having two adjacent edges discontinuous, okay, or we have one short edge discontinuous and so on, right? So that is the type of support condition, especially if we are dealing with a two-way slab. Okay, then the continuity of the slab, right? So this is actually considering whether it is connected to just one slab. Okay, the beam is connected to just one slab on one side, or it is in contact with the slab on both sides, right? Ada dua, kiri kanan, both sides. Okay, so we need to look into that as well. Okay, so for rectangular slabs that is supported in four sides, okay, the following method can be used. Okay, whereas we have one-way slab, okay, where Ly over Lx is more than 2, right? Okay, so this is if we are dealing with a one direction load transfer. Okay, right? So this is one case. So we have one-way slab with Ly over Lx larger than 2, right? So it can actually be calculated, okay, simply by using this calculation. Okay, whereas we are going to have, if we are designing or transferring the loads, okay, for beams AB and also CD, okay, which are these beams. Okay, so we have this beam and also this beam, and we have a slab that is a one-way slab, therefore the direction of the loading will be transferred only in one direction. Okay, so you can see here that we have these arrows. So these arrows are actually showing us the direction of the load transfer, right? So only beam AB and also beam CD will be taking the loading from the slab. However, as for beams AB, beam AC, okay, and also beam BD, right? So it will not take any loadings from the slab, right? So you can see from the calculation, okay, is that for beam AB and CD, we have NLX square over 2, okay. Then as for beam AC and also BD, right? So as for this, we are not going to have any loadings transferred from the slab, right? Okay, so you have to know this. You have to know the direction of the loadings, okay? So we can either, okay, use the this basic calculation, okay, or we can also use the shear values in at the beam support, okay, which is determined using the um, table 3.12 KBS 8110. Okay, so that is for a one-way slab. Okay, so the next one is for a two-way slab, right? So for a two-way slab, okay, so therefore, since it is catering for a two-directional forces, right? Okay, so therefore, with regards to the distribution of the loadings, also we need to consider two directions. Okay, right? So it can be calculated using this equation, right? So these are the basic equation for the equivalent UDL. Right, so we can see from the figure, okay, is that for beams AB and also beam CD, right? So beam AB and also beam CD, it can be calculated, okay, using this equation, okay, whereas we have NLX over 3. So we are actually considering the transfer that is from these two trapezoidal shape, right? Okay, so that is for beam AC and BD. Then, however, for beam ABCD, uh, oh, sorry. Okay, so this is for beam ACBD, right? Okay, so this top part, right? So ACBD, which is this one. Okay, and then as for beam ABCD is this one. Okay, this one. Okay, right? Okay, so and you can see that the calculation is quite detailed, okay, with regards to the ABCD, right? Okay, so this is for the load transfers, right? So you can see that for these two directions, slabs, okay, and the load transfer, okay, will be different, right? Okay, because it is transferring a different value of loadings, okay, and we can either use that method, okay, using the equivalent equation, or we can also use the shear values at the beam support, right? Okay, so for the shear values at the beam support, it can be actually determined using table 3.15, right? So this method provides more accurate assumption on the distribution of the loading from the slab, because the factors on the continuity of the slab and the support types have been considered in the provision clause, right? Okay, so the table that we will be referring to, okay, right? So if we refer back to our design appendix, Okay, right. So we have our design appendix, right? And then we refer to table 3.15. Okay, so this is table 3.15. Okay, right, which gives us the shear force coefficient for uniformly loaded rectangular panels. Okay, supported on four sides for provision for torsion at corners. Right. Okay, so we can actually calculate the design loads on beams supporting the solid slabs, spanning in two directions at right angles, and supporting uniformly distributed loads. So we can actually use this equation, which are Vsx and also Vsy, in order to determine the values, of the transferred loads, and the value for beta Vy and also beta Vx can be determined from this table, right? Okay, so if you still remember previously in our calculation, for the slab design, we have already used this table for the shear force coefficient, right? So, and we are going to use this again, but this is on the load transfer to the beam, right? Okay, so similarly, we will be referring to the type panel or and location. Okay, so we have this. We have the type of panel, and also the location, right? So you have to look into the continuity of your slab, right? So which part is continuous, which part is discontinuous. So the method to determine that is similar to the slab design. Okay, right. So if we go back to our lecture slide, right? So loads on supporting beams, right? So these are the two equations, that I have already mentioned just now, right? So basically, we are going to use that with the value of N, which is the loading that is acting on the slab in kilonewton per meter square, right? Okay, so basically we have already covered all, with regards to the basics of a reinforced concrete design, right? Okay, so for the next topic, we are going, for the next part, we are going to look into the example, which will be covering on the analysis of the loadings, as well as the load transfer, and also the design of the reinforcements, up to the drawing the detailing for your beam, right? Okay, so let's end our class here, right? Okay, with Tasbih Kifarah and Surah Thomas. All right, thank you very much, everyone. Assalamualaikum.